the next one, your equation of your isothermal process. Yeah, so how you can define the equation of your isothermal process over here. So that is what we can see over here. So the ideal gas equation for n moles of a gas, so PV is equals to nRT. So this is, I told you, in isothermal process the temperature of the system will remain constant. So you have to make the wall of this system conducting, so that there is an exchange of heat with the surrounding, so which will make sure that the temperature will remain constant. So that is nothing but your isothermal process. So obviously in that the pressure is inversely proportional to volume, and this is PV is equals to constant. Again, this is also a very slow process. So this isothermal process is also a very slow process. So the next thing, actually you have to now apply the first law of thermodynamics to the isothermal process. Yeah, so what you can write it down from that. So if I just say that, so this delta Q is equals to delta U plus P into delta V. Yeah, so this is nothing but what we know about this, your first law of thermodynamics applied to the isothermal process. So in this case, obviously we have seen that your temperature is going to remain constant for this particular case over here. So this is how we can write it down, that your first law applied to the isothermal process. Delta Q is nothing but the amount of heat provided. So part of the heat we are going to utilize to increase its internal temperature, that is a delta U. Again, part of the heat we utilize to do some work. Now the work done by the gas, yeah, on this piston, and the piston will move in the upward direction. So definitely this piston will move through this, let's say the distance dx. So that's why we had just written over here. So this delta V is equals to actually your A into dx. Yeah, so that is nothing but the change in the volume over here. So this is delta Q is equals to delta U plus P into delta V. So that is how you can apply that first law of thermodynamics to the isothermal process. Now for this case, we can find the work done in the isothermal process also. So how we will find that work done for this particular case, now that we will study. So the work done, we know that, so this W is equals to PdV, again which is from V1 to V2 over here. Now next thing what we can do over here, so you have to just write it down, that formula for this. So this one again you can write it down in terms of this PV is equals to RT. Yeah, so this PV is equals to RT. So P is equals to, again that is a RT upon V. So this work done is V1 to V2, again this is RT upon V, and then again this one you can write it down, that is a dV. So RT again V1 to V2 dV upon D. Again taking the integration on both the sides, so you can write it down, that is a ln of V2 minus V1, and this one you can write it down 2.3 RT, that is a log of your V2 minus V1. Yeah, so this is how we can write down the formula for your work done, which is 2.3 RT log of V2 minus V1, which is the work done in case of your isothermal process. So that is your formula for this one. So again obviously just we told you that, so work done is nothing but the work done by the gas over here. So when it get expanded, and it will just push that piston upward through certain distance. So that is what we can call about the work done in the isothermal process. So in case of isothermal process, still one more interesting thing, when you apply that first law of thermodynamics, this is what I have written, delta Q is equals to delta U plus P into delta V. Now since temperature is constant, so I am saying that the temperature is constant, where the internal energy of the system, it depends on the obviously the temperature. Yeah, so if I increase the temperature, the internal energy is going to increase. Yeah, so definitely over here the temperature remains constant. Yeah, so this delta U, you can say that it is 0 since there is no increase in the temperature. So straight away I can write it down, that delta Q is equals to P into delta V. Again one more thing over here, if you compress that gas, if you are compressing that gas slowly, so obviously the delta Q becomes, that work done is negative. So the delta Q is less than 0 in case of compression, and in case of expansion obviously the work done is positive, so the delta Q obviously again that is nothing but positive. Yeah, so this is how you can say about in case of your compression as well as that is nothing but your expansion of the gas when you apply the first law of thermodynamics to that your isothermal process over here. And for this case the work done you can write down for n number of moles also, yeah, or either you can just take, let's say for example if I consider 1 mole, so then I have written that RT. Yeah, so in general you can write it down that n also. Yeah, so that is not an issue. So this is how we can write it down, this is n. Yeah, so just you can replace n over here and you will get the required formula for that your work done.